Alright, so today we will be solving the February March 2026 paper 2 of AS Physics, okay? So let's get started with the first question. Define force. Force is the rate of change of momentum, okay? So you should know these definitions. Now part B says use the definition in part A to show that the SI base units of force are kilogram meter per second squared. Alright. So in part A we said that force is the rate of change of momentum, okay? This is what we said, okay? Now momentum is the product of mass and velocity. So m delta v because change in momentum over delta t. Alright. Now in SI base units, for mass it's kilogram, for velocity it's meters per second, time is just second, okay? Now let's move the second up, okay? Now this becomes kilogram meters per second squared, alright? So hence shown. Now part C. Alright, let me summarize this, okay? They gave you an equation, okay? V is the velocity, alright? F is the force applied, K is a constant with SI base units, this, alright, they showed us. M is the mass, A is the cross-sectional area. Now by considering the SI base units on both sides, they want us to check whether the equation is homogeneous or not, alright? So let's do that. Now for velocity, the SI base unit is meters per second, okay? Meter second inverse. Force, we just found it, okay? Kilogram meters per second squared. Kilogram meters per second squared. And for K, by the way, they gave us, it's meters squared second inverse, okay? Now in the denominator, mass is just kilogram, area is meter squared, okay? Now let's check out how can we simplify the right hand side, okay? So we can cancel out kilogram and kilogram, okay? And this meter squared and this meter squared also cancels out, okay? So the left hand side stays at as it is, okay? Meters per second. Whereas the right hand side simplifies to, see, there's meters, okay? And this second to the power of minus 2 and second to the power of minus 1. So we can add the powers, okay? S minus 2 minus 1, this becomes S minus 3, okay? Because they are like terms, okay? So I hope you get this. So this becomes meters second to the power of minus 3. Now we can say that the equation isn't homogeneous. Why? Because left hand side is not equal to the right hand side, okay? So that's it for question number 1. Question number 2. State the principle of conservation of momentum. Okay. So total momentum of all bodies before after collision remains conserved, but only if conserved provided that no external resultant force acts upon them. Alright, so you should know the definitions by now. Part B. Alright, so they say that a stationary boat of mass 160 kg floats on water. Alright, blah blah blah, and there's a sack of mass 23 kg thrown at the boat. Alright, immediately before colliding with the mast of the boat, the sack is traveling horizontally with a speed of 3.4 meters per second, okay, and it's shown on the diagram as well. Alright, and by the way, they said that the boat is stationary, okay, so initially it has zero velocity, it's at rest. Alright, so I think we have enough on information, okay. Part I says that calculate the horizontal speed v of the sack and boat immediately after the collision. Alright, by the way, the sack collides with the mast and remains in contact with it without rebounding, okay. So before the sack was moving towards the boat, okay, the mast of the boat, and the boat was at rest. Now what happens after is that this is the boat, alright, and the sack is part of it now, okay. So the combined mass into the velocity, okay. I hope you get the clue from here, okay. Obviously we are going to use conservation of momentum, okay. So let's do that. Initially the boat was at rest, so it has zero momentum, okay. Whereas for the sack, m let me write it, okay. Mass of boat, v of boat, plus mass of sack, v of sack, is equal to, they combine, okay. So mass of the boat plus mass of the sack into v, okay. The v is the same, okay. It's a common velocity for both of them. They move at the same velocity, okay, same speed. So anyways, this is 0 because at rest, okay. So mass of sack was, let's just find the velocity directly, okay. Let's not waste time. 23 into 3.4, I think, yes, over the mass of boat plus mass of sack. So 160 plus 23, okay. Let me put this into my calculator. 23 into 3.4 over 160 plus 23. This gives me an answer of 0.43 meters per second, okay, to two significant figures. Alright, next, the total kinetic energy of the sack and boat immediately after the collision is E1. Okay, so after the collision it's E1. The total kinetic energy of the sack and boat, oh wait, my bad, E1 is immediately before the collision, okay, and E2 is after the collision, immediately after the collision, okay, my bad. So by the way, what energy is it? It's the kinetic energy, okay. So let's calculate E2 first after the collision, okay. It's gonna be half, by the way, kinetic energy is equal to half mv squared, okay. Just wrote the general form. After the collision, we know that the masses were combined, so 160 plus 23, the velocity we just found out to be 0.43, okay, 0.43 whole squared, okay. Let's leave it as it is. Now let's find E1. uh, the boat was at rest, okay, so it will have zero kinetic energy, whereas the sac, half into m of sac, which is 23, into velocity of sac was 3.4 whole squared, okay. So E2 over E1, just substitute them, okay. Just put this into your calculator, okay. So let me just write it out so you guys don't get confused. To 160 plus 23 into 0.43 whole squared over half into 23 into 3.4 squared, okay. Half and half cancels out, okay. So you can just directly substitute this into your calculator. 23 into 3.4 whole square, okay. So I get an answer of 0.13 to two significant figures, okay. So 0.13. Next, state and explain whether the collision between the sac and the boat is elastic or inelastic. Straight away, it is inelastic. Why? So whenever the answer is inelastic, the answer is pretty simple, okay. The explanation: kinetic energy is not conserved, okay. Or better to say that kinetic energy before and after are not the same. It's basically the same thing, okay. So if you notice that kinetic energy initial, which was E1, and E2, they're different. That's why there's a ratio, okay. Obviously there's a ratio because they're different, okay, or else it would have been 1. So the ratio isn't equal to 1, meaning that E2 and E1 are different, okay. The kinetic energy is not conserved, so it's inelastic collision. Now part C says that after a short time the boat in part question 2b is at rest again. Show that the upthrust acting on the boat with the sac is 1800 newtons. Alright. Now if you notice that, let's go back, okay. This boat over here is at equilibrium again, okay. It's at rest. Now when it's at rest, the weight of the boat plus sac, weight of boat plus weight of sac, because it's part of it, okay. The sac is part of the boat now, okay. So this must be equal to the upthrust, okay, upthrust. So simply from there we can find that the upthrust U is equal to the combined mass, okay. Wait, let me write weight of boat plus weight of sac, which will be equal to the mass of the boat plus mass of the sac into G, which is 9.81, okay. And if you do that, you will get an answer approximately 1800 newtons, okay. Now part II, the boat displaces water with a volume of 1.80 times 10 to the power of 5 centimeter cube, okay. So straight away, one thing you should keep in mind is this is not an SI unit, okay. So we have to convert it to meters cube, okay. Calculate the density of the water. Give your answer to three significant figure, okay. Now another equation, upthrust is equal to rho of liquid times V of liquid displaced, okay, they already gave us, times G. So you should know this equation also. Upthrust is 1800 newtons. The density of liquid, what is the density of liquid? They give us, let's find it out, okay. So I think it's water, yeah. So it's gonna be, yes, it's water. Oh, wait a second. The question itself is asking us to find the density of the water. My bad, okay. So I don't know what happened to me today. Anyways, the volume of liquid is going to be 1.80 times 10 to the power of 5 times 10 to the power of minus 6, okay. Why 10 to the power of minus 6? It's because 1 meter is 10 to the power of 2 centimeter, okay. 1 meter cube is going to be 10 to the power of 2 whole cube centimeter cube, which is further 10 to the power of 6, okay. So from meter cube to centimeter cube, you multiply with 10 to the power of 6. From centimeter cube to meter cube, you multiply with 10 to the power of minus 6, okay. So I hope you know the conversions, okay. I shouldn't be explaining this. So anyways, from here, rho of liquid is going to be, let me plug this into my calculator, 1800 over 1.80 times 10 to the power of minus 1, okay, times 9.81. This gives me an answer of 1019 kilogram meter cube, inverse cube, okay. So to two significant figures, okay, we can write, oh wait, three significant figures, okay, three significant figures, because they want us to write it in three significant figures. We can write this as 1020, okay, 1020, okay. So that's it for question number 2. Question number 3. A roller coaster carriage of mass 280 kg travels over a raised section of a track as illustrated, blah blah blah, okay. At position X, the carriage has a kinetic energy of 16.1 kilojoules, whereas at position Y, the carriage has a kinetic energy 1.3 kilojoules, okay. So straight away we can notice that kinetic energy is lost, okay. So we can notice that, okay. The length of the track between X and Y is 23 meters, okay. So this thing over here is 23 meters, okay, the length of it. In moving from X to Y, the carriage does 5.1 kilojoule of work against resistive forces. Part A. Calculate the average resistive force acting on the carriage between X and Y. Okay, this is easy. Work done is equal to force into distance, okay. So they gave us that 5.1 times 10 to the power of 3, because kilojoules, okay, is equal to force into the length of the track, which is 23, okay. So force from here is equal to, let me put this into my calculator, 5.1 times 10 to the power of 3 over 23, it is equal to 221.7, approximately 220 newtons, okay, to two significant figures, 220, all right. And by the way, that is the resistive force which we found out, okay. Now part II, calculate the change in height delta H between X and Y, okay. So they want delta H, okay. And by the way, as we said that there's a loss of kinetic energy. Okay, so the loss of kinetic energy is going to be equal to the gain in GPE. Okay, because it's going up. Okay, the GPE increases because the height increases from x to y. Okay, plus the work done against resistive forces, which is already given. Okay, 5.1 kilojoules. Anyways, let's write that. So first of all, we are going to write that loss of kinetic energy is equal to gain in GPE plus work done against resistance. Okay, now what is the loss of kinetic energy? It's the kinetic energy initial minus final. Okay, and we have to multiply that by 10 to the power of 3 because it's in kilojoules. So 16.1 minus 1.3 into 10 to the power of 3 is equal to gain in GPE, which is going to be mass, which is 280 kg. Okay, 280 into G, which is 9.81, into delta H, which we have to find. Okay, plus the work done against resistance, which is 5.1 times 10 to the power of 3. From here, delta H is going to be equal to, wait, what is 16.1 minus 1.3? It is 14.8. Okay, so it's 14.8 times 10 to the power of 3 minus 5.1 times 10 to the power of 3 over 280 into 9.81. Okay, let me put this into my calculator. Minus 5.1 times 10 to the power of 3 over 280 into 9.81. Okay, so this gives me an answer of 3.53 meters. I'm gonna write it to two significant figures, so 3.5 meters. Okay, now part B. The carriage travels further along the track to point Z. State and explain whether the speed of carriage at Z is greater than, less than, or the same as the speed of the carriage at X. Alright. So the carriage over here, it moves to Y, yeah? And from there we said that there's a loss of kinetic energy and blah blah blah, whatever. Okay, now they're saying that the same carriage now moves to a point Z over here. Okay, now look, if there weren't any resistive forces, okay, suppose there were no resistive forces, now all of the kinetic energy would have been converted into gravitational potential energy, and then the same gravitational potential energy would have been converted to kinetic energy again at Z. Okay, so then in that case the speed would have been the same and the height is also the same. Okay, X and Z are at the same level. Okay, so then in that case uh, Vz would have been equal to Vx, but in this case energy is being lost in doing work against resistive forces. Okay, because there's friction over here. Not all the kinetic energy is being converted into GPE because there is energy lost. Okay, there's energy lost. So what we will have to write over here is speed of carriage at Z. I'm going to write it in short form. Okay, is less than speed of carriage at x, because energy is lost in doing work against resistance. Okay, so I hope that made sense to you guys. So that's it for question number 3. Question number 4. A uniform square picture is attached to a wire and hangs in equilibrium from a pin at point P, as shown in figure 4.1. Alright, so let me just give you the key information. Okay, the picture has a weight 19 Newton, center of gravity is directly at below P. Okay, so this is the center of gravity, and they said that the tension in the wire is 13 Newton. Okay, and the wire forms an angle of theta with the horizontal, which is shown. Okay, theta. So that's the key information. Now part A, I define the moment of a force about a point. Okay, product of force and perpendicular distance from point of application of force to the pivot or axis of rotation. Alright, now the second part says that explain why the moment of the weight about P is 0. Alright, let's look at the diagram now. This is the weight acting downwards, yeah? This is the center of gravity. And P is the pivot, okay? Now look at this. If you draw the line of action of force, it passes through P, which is the pivot. And whenever the line of action of a force passes through the pivot, the perpendicular distance is equal to 0. And we know that moment is equal to force times d perpendicular. If d perpendicular is 0, then moment is equal to 0. Alright? So I hope that makes sense. So let's write it down, okay? Line of action of weight passes through P, so perpendicular distance is equal to 0, therefore moment equal to 0. Okay, I wrote it in short form because I don't have enough space. So I hope you got the idea. Okay, now calculate theta. Okay, now let's move back. Okay, they said that the picture hangs in equilibrium from a pin at point P. Okay, so it's in equilibrium. Now whenever it's in equilibrium, the upward forces must be equal to downward forces, and F right should be equal to F left. But we are going to focus on this point over here. F up is equal to F down. What do you see downwards? It's the weight. What do you see upwards? It's the tension, okay? The tension. Now, there are two tensions over here. But is it the tension specifically? No. It's the vertical component of tension. Okay, this is going to be T sine theta. Yes, T sine theta. And same over here, okay? This is going to be T sine theta. Okay, now 2t sine theta is going to be equal to the weight, okay, because there are two tensions. Now let's go back. 2t sine theta should be equal to the weight, okay. Now sine theta is going to be equal to the weight, which is 19, I think. Weight, yes, 19, and they gave us tension is 13. 19 over 2 times 13. So from here, theta is equal to sine inverse of 19 over 26. Okay, let me plug this into my calculator. Sine inverse of 19 over 26. This gives me an answer of 46.95. Okay, 46.95. So approximately 47 degrees. Okay, 47. All right. Part IV says that the wire has diameter 0.80 millimeter and is made of a metal with Young modulus 9.3 times 10 to the power of 10 pascals. The wire obeys Hooke's law. Calculate the strain in the wire. All right. Now Young modulus, okay, let me write it as E is equal to stress over strain, and from here strain is equal to stress over E. Now what is stress? It is force over area, and over here the force is the tension. So tension over area is pi r squared over E. Alright, Young modulus. Now r is equal to diameter over 2, so 0.40, and times 10 to the power of minus 3 meters, okay, because they gave us in millimeters, right? So this is going to be equal to 13 over pi into 0.4 times 10 to the power of minus 3 over the Young modulus, which is 9.3 times 10 to the power of 10. So plug this into your calculators. Okay, 13 over pi into 0.4 times 10 to the power of minus 3 whole squared, okay, I forgot that, over 9.3 times 10 to the power of 10. Okay, so I get an answer of 2.8 times 10 to the power of minus 4. Okay, to two significant figures, 2.8 times 10 to the power of minus 4. And by the way, notice that we have no units. Why? Because stress is also given in pascals, okay, and Young modulus is also given in pascals, okay, so they both cancel out. Strain anyways does not have any unit, okay, so that's why there is no unit. Okay, now over here in part B they say that the bottom side of the picture shown is 1.6 meter above the ground. The pin at P breaks. Okay, now it breaks and it falls vertically downwards. Resistive forces are negligible. Calculate the time taken for the bottom side of the picture to hit the ground. Alright, so over here we are going to use S is equal to UT plus half AT squared. Okay, S is going to be 1.6 meters, and this part over here is just going to be 0, okay, because initial velocity is going to be 0. Okay, equal to half into 9.81 t squared. Okay, now why is initial velocity 0? Okay, because some of you might be thinking it's because that it was initially at equilibrium. Okay, it was held at a point P, and then all of a sudden it just falls. Okay, so initial velocity is 0. Okay, so t is going to be radical 1.6 times 2 over 9.81. Alright, what is this? It's going to be 3.2 over 9.81. So I get an answer of 0.57 seconds, okay, to two significant figures. 0.57. Okay, part II. On figure 4.2, sketch the variation of speed of the picture with the distance fallen from its initial position. It's not time, it's distance, okay? Now, one thing, when the picture falls, okay, this is the picture. This is the ground, suppose, okay, yeah, let's take this as the ground, okay? As it falls, the what you call mgh is being converted to kinetic energy. Okay, loss of mgh is equal to the gain in kinetic energy, and they already told us that resistive forces acting on the picture are negligible, so obviously there is no work done against resistance. Okay, all right. Now mgh is equal to half mv squared. M and M cancels out. Now let's find V. V is equal to radical 2GH. Okay. Now why did I find out V? Why not any other variable? It's because V is on the y-axis. Okay. It's as if you're forming an equation. Now from here, let's find V at D equal to 1.6, okay, or h equal to 1.6. Now that is going to be radical 2 times 9.81 times 1.6. Okay, now what is that equal to? Let me plug that into my calculator. That is equal to 5.6 meters per second. Okay, so keep that in mind. Now another thing is, what is the relation between speed and distance from this equation? The distance is the height in this case. V is directly proportional to radical h, okay? Because you take the square root. Anyways, we took that, okay? So from here we know that it's a square root function, okay? And by the way, initially we know the speed was 0, and when the distance is 0, the speed is 0, so it starts from the origin. Okay, and we found out that the speed at 1.6 meter was 5.6. okay, let's label the point somewhere over here. Okay, it's a rough sketch, and we know that it's a square root graph. Okay, so the gradient is going to decrease. Okay, you should know the square root graphs, quadratic, and those stuff by now. So it's going to be something like this. Okay, the gradient should decrease. So that's it for question number 4. Question number 5. For a progressive wave, state what is meant by period and amplitude. Okay, so period is the time taken for one complete oscillation. Okay, whereas amplitude is the maximum displacement from mean or equilibrium position, from equilibrium position. Alright, now part B, let's just skim through it. Okay, blah blah blah. Frequency is 25 hertz. A stationary wave is formed on the string. Distance between two fixed ends of the string is 0.96 meters. Okay, so the length is 0.96 meters. Okay, now part I, draw a cross at the position of an antinode. We said that antinode is the no, that was amplitude, never mind. But antinode is also maximum displacement. Okay, so the maximum displacement is this, it is this, it is this. So these are the antinodes. Okay, whereas the nodes are zero displacement positions, so these are the nodes. Okay, so I hope you get that. So let me draw a cross over here, antinode. Okay, yeah, that's it. Now part II says that show that the speed of a progressive wave on the string is 16 meters per second. Now V is equal to F lambda. Okay, so this is the main equation. Now what is the wavelength? Okay, one thing to notice is you will see that this is one wavelength. Yes, this is one wavelength, this is lambda, and there is this thing also, this is half lambda. If you see, yes, if this whole thing is lambda, then this thing specifically over here is going to be half lambda. Okay, half lambda. So this is going to be lambda plus lambda over 2, which is going to be 1.5 lambda. Okay, so I hope you get that. So 1.5 lambda is equal to the length, which is 0.96 meters. So lambda is equal to 0.96 over 1.5. Okay, so what is this? 0.96 divided by 1.5, which is 0.64. 0.64 meters. Okay, so V is equal to the frequency, which is 25 hertz, okay, into 0.64. Okay, and this should give us an answer of 16. Let's double check. 25 times 0.64, yes, this gives us 16 meters per second. Okay, so hence shown. Now the next part, the frequency of vibrations is increased to 30 hertz. The speed of the wave on the string does not change. State and explain whether a stationary wave is formed. Okay, again, V is equal to F lambda. Okay, and from here they said that the speed does not change. So what is lambda? Lambda is equal to V over F, so 16 over 30. Okay, what is 16 over 30? This is 0.533 recurring. Okay, 0.533 and so on. Okay, now for stationary waves, and since it is fixed, okay, fixed ends, the length of the string should be an whole number multiple of half the wavelength. Okay, remember this thing. Now let me show you how. Originally, okay, for the original string, okay, when the frequency was 25 hertz, okay, this was the wavelength. Okay, now let's double check. For a stationary wave to be formed, L should be a whole number multiple of half the wavelength. So 0.64 over 2, which is 0.32 meters. Okay, now 0.96 over 0.32 is equal to 3, which is a whole number. So that's why a stationary wave is formed. Okay, now let's check for this one. uh, it's going to be half wavelength. Okay, so directly we could just find n also. Yeah, so n is equal to L, which is 0.96 over lambda over 2, which is going to be 0.533 over 2, and this gives me an answer of 3.6. This is not a whole number, not a whole number. Okay, so hence or therefore stationary wave does not form. Okay, I hope you understood this point. Now part C, okay, this is a diffraction grating question. Okay, they gave you the wavelength, which is this, and this is not d. Okay, this is n, the lines per meter. Okay, they gave you theta, which is 37 degrees on the diagram. Okay, and they also told you. Okay, now part I, calculate the order n of the bright spot formed at x. Okay, so diffraction grating, the main formula is d sine theta is equal to n lambda. But we have a problem. They never gave us d. They gave us n. This is n. Okay, so from here the relation between d and n is d is equal to 1 over n. Okay, which is equal to 1 over, what was n? 6.7 times 10 to the power of 5. 6.7 times 10 to the power of 5. Yes, 5. Alright, so n is equal to d. Just substitute it as it is. 1 over 6.7 times 10 to the power of 5 into sine 37 over lambda, which was 4.5 times 10 to the power of minus 7. 4.5 times 10 to the power of minus 7. Okay, let me plug this into my calculator. 1 over 6.7 times 10 to the power of 5 into sine 37 over 4.5 times 10 to the power of minus 7. So I get an answer of 1.996. Okay, 1.996. Okay, but n is always a whole number. Okay, so we have to round it, so it's really close. Okay, so it's approximately 2, so n is equal to 2. All right, now part II, the diffraction grating is replaced by a grating with fewer lines per meter. Okay, n changes. Alright, state whether the distance between adjacent bright spots on the screen increases, decreases, or remains the same. Alright, so n decreases. Okay, n decreases, and d sine theta is equal to n lambda. So d is equal to 1 over n. If n decreases, d increases. If d increases, now look at what happens to sine theta. Okay, sine theta is equal to n lambda over d. So d increases, sine theta decreases. And if sine theta decreases, then I think it's lagging. Okay, so sorry for that. Theta decreases. Okay, so that's the thing. Now let me show you on the diagram as well. See, if theta decreases, the angle was 37. Okay, now suppose it's like 20 maybe. Okay, so look, the distance between the maximas or adjacent maximas decreases. Okay, one is going to form down over here also. It decreases, okay? The distance decreases compared to the, suppose this one, okay? The original one. Look at the distance. It has decreased significantly, yes? So that's the key over here. And they just told us to state, okay? So we say that distance between, we have to just state it. They never told us to explain adjacent bright spots, bright spots decreases. Alright, so that's it for question number 5. Alright, so question number 6, part A. State what is meant by an electric current. Okay. Rate of flow of charges. Okay, so you have to know these things. Now part B. Alright, they just gave us key informations. Okay, EMF is 1.50 volts, internal resistance is 0.75 ohms, and current is being varied from 0 to 1.6 amperes. Alright, and they want us to draw the variation of terminal potential difference with the current. Alright, now terminal potential difference VT, V terminal, is equal to the EMF minus the voltage lost, okay, or the voltage across the internal resistance, which is the current times the internal resistance. Okay, so this is the key equation. Okay, now when I is equal to 0, I times small r, the voltage across internal resistance is going to be 0, so the terminal voltage is just the EMF. Alright, so at 0 current it's 1.5. Alright, now when I is equal to 1.6 amperes, okay, then there is obviously going to be a non-zero value. Okay, so 1.6 times 0.75 is going to be 1.2. Okay, 1.2, so VT is going to be 1.5 minus 1.2, which is going to be 0.3 volts. Okay, now 0.3 volts, let's zoom in. Okay, so we have 10 blocks. Okay, 10 blocks over here, 10 tiny blocks, which gives us 0.5. So one block is 0.05 then. Alright, so this is going to be the midpoint 0.25, this is going to be 0.3. So that is the other point which we needed. Okay, and from here we just draw a straight line connecting both the points. Now why a straight line, why not curved? That is because of the equation. V terminal is equal to the EMF minus IR. This is a linear equation, linear relationship. Okay, so that's why it's a straight line. So I hope you got that point. Now part C. Alright, let's skim through it again. Okay, no need of reading it all. Wire X, length is 6.8, cross sectional area is this, resistance is 0.82. Alright, and there is internal resistance also. Okay, there's again voltage being lost, there is the EMF, this is the main current. Okay, and you will notice that the current splits over here. Okay, I1 maybe or IR. Okay, I passing through the resistance and I passing through the wire X. Okay, so that was basically the summary. Now part I, calculate the resistivity of the metal from which wire X is made. Now R is equal to rho L over A. They want rho, resistivity, okay? Rho is going to be the resistance, which is 0.82, okay? 0.82 into the cross-sectional area, which is 2 times 10 to the power of minus 7, 2.0 times 10 to the power of minus 7 over the length. What is the length? I think it was 6.8 meters. Yes, 6.8 meters. Now let me plug this into my calculator. Alright, so I get an answer of 2.4 times 10 to the power of minus 8 ohm meter. Okay, 2.4 times 10 to the power of minus 8. Alright, now part II. Calculate R. Alright, now here comes the twist. Okay? Now you'll notice that there is voltage getting lost, okay, to the internal resistance. This is small r, which is 0.75, and there is V lost, okay. The rest travels, okay. It doesn't travel like it is volts, okay. The remaining volts is going to be the terminal potential difference, and it's going to be equal, okay. V terminal is going to be V of fixed resistor, which is going to be V of X. Why? Because they're connected parallel, and in parallel the voltage remains the same. Alright, but they want us to calculate R, the resistance, okay, resistance of the fixed resistor, and we can find the terminal potential difference. But what about the current? The current splits, okay, IR and IX, okay. Now IR, we have to find IR in order to calculate R, okay. R is going to be V terminal over IR, okay. So we have to find IR first. Let me label it. This is going to be IR and this is going to be IX, okay. Now we can find Ix because we have the resistance 0.8 ohms, okay. Now wait, let's find V terminal first, which is going to be the EMF, which is 1.50 minus 1.8, the current, okay, into 0.75, I think. Yes, 0.75, okay. What does this give me? Wait, 1.5 minus 1.8 into 0.75. This gives me 0.15 volts, okay. And this is going to be equal to Vx and Vr, okay. Now, as for wire X, we have to find the current passing through X, okay. The current passing through X is going to be Vx over resistance of X, okay, Rx. Now Vx is the same as the terminal potential difference, which is 0.15, and Rx, resistance of X, is 0.82. Alright, so what is IR? Now by Kirchhoff's first law, 1.8 is going to be equal to Ix plus IR, okay. And we found out Ix. I just left it like that, okay, so our answer is more accurate. IR is going to be 1.8 minus Ix, okay. Now from there we can find R. R is going to be V terminal over IR, okay. So the terminal voltage, which is 0.15, over IR, which is 1.8 minus 0.15 over 0.82. Let me plug this into my calculator. Okay, 0.15 over 1.8 minus 0.15 over 0.82. So this gives me an answer of 0.093 ohms, okay, to two significant figures. 0.093. Alright. Now the last part of the question, calculate the power dissipated in the internal resistance of the cell. Let's go back. Internal resistance, okay. So the current that passes through it is 1.8 amperes, okay, because current then joins again over here, okay. So it's the same 1.8 amperes, and we have the internal resistance R, okay. So we can use P is equal to I squared times R. P is equal to I squared R, which is going to be 1.8 squared times 0.75. Okay, 1.8 squared times 0.75. This gives me an answer of exactly 2.43 watts. To two significant figure, I'm going to write it as 2.4. Okay, that's it for question number 6. Alright, question number 7, part A, describe the structure of a nuclear atom. Alright, so protons and neutrons are present in a small dense nucleus, and electrons orbit around the nucleus. Okay, so this is basic stuff. Now part B, P and Q are radioactive nuclei. P has 94 protons, Q has 91 protons. Each nucleus decays to form a nucleus with 92 protons. Okay, so they're basically just asking the type of radioactive decay experienced by P and Q. Okay, now the first thing, let's talk about P. P has 94 protons, okay, and it goes to form, let's name this, what do we name it? A. Okay, it forms A with 92 protons, okay, plus some particle, we don't know that. Now same for Q. Okay, Q has 91 protons and it forms A with 92 protons plus something. Okay, we know that the charges must be balanced, the number of protons. Okay, so therefore it's going to be alpha. Okay, because alpha has 2, so 92 plus 2 is equal to 94, so therefore it's going to be alpha decay. Okay, now over here it's going to be a beta minus decay. Okay, 0 minus 1, because 92 minus 1 is equal to 91. Alright, so we have to write beta minus. Okay, I think they just want us to write state the type of radioactive decay, so beta would be enough, I think, but it's better to write beta minus. Okay, the examiner won't deduct marks for anything that is extra, but if something is less you won't get the marks, so it's better to write beta minus dk. Now next, okay, part C, particle X has a ratio of charge to mass equal to 1.76 times 10 to the power of 11. Identify particle X. Now this is a trial and error, okay, question. We don't know anything, they just gave us that the charge to mass ratio is this. We have to find it, okay, through trial and error, okay. Now suppose we have, let's list them down: proton, neutron, electron, positron, okay. These are the common particles we know, okay. It can't be neutron, immediately eliminated. Why? Because neutron does not have a charge, so its charge to mass ratio is going to be 0. Now for electron also we can eliminate it, because the charge to mass ratio, it's positive, it's not negative, okay. So electron is negative, so we cancel that, okay, eliminate it. Now the answer over here is positron. Why positron? Okay, because the charge to mass ratio is equal to 1.6 times 10 to the power of minus 19 over 9.11 times 10 to the power of minus 31, and that gives you an approximate answer of 1.676 times 10 to the power of 11 coulomb kg inverse. Okay, now where then I get these values randomly? Okay, just go back, okay, let's go back, and you'll find them over here, okay. Rest mass of an electron and the unified atomic mass unit, okay, that is there, and this one, okay, elementary charge, we are talking about charge over here, okay, and rest mass of an electron. Now let's try with proton, okay. Rest mass of a proton is 1.67 times 10 to the power of minus 27, okay. Let's go back, 1.67 times 10 to the power of minus 27, remember that, okay. Proton, okay, so the charge to mass ratio again 1.6 times 10 to the power of minus 19 over 1.67 times 10 to the power of minus 27, and let me just put it into my calculator, okay. Over 1.67 times 10 to the power of minus 27, you will notice that it's a value, okay, it's a really large number and it's not equal to the one we are told to, okay. So that's why it's a positron, okay. So we can eliminate proton also. Alright, so that's it for this question paper.